Alright, it is finally time to wrap up our work on Chapter 8. I know this has been very long and drawn out. We began this chapter prior to senior service, took a little break for the juniors, and then of course we had all this COVID-19 mess. But finally it looks like we're going to be able to finish up Chapter 8. Now, the first section we covered what exactly a chemical reaction is, and the second section we covered how to balance. So finally, to wrap up, we're going to talk about how we will classify these chemical reactions and what makes each of them different from each other in some capacity. So there's no place to start like the simplest, so we're going to begin with what are called synthesis reactions. And I want it noted that these can also go by the names of composition and they can also go by combination. But a synthesis reaction is one of the simplest types of reactions, and in most cases, a single compound will form from the combination of two or more different reactants. So, for example, when two elements react with each other, in this case we've got carbon reacting with oxygen, forming the singular compound of carbon dioxide. An alternative to this process, especially when things are inefficient, could be carbon and oxygen instead forming carbon monoxide. But in both cases, we have two elements, each reacting with each other and forming a singular compound. And in this case, these are known as binary compounds because binary means two. In some cases, synthesis, which is the term I most often like to call it, if both reactants are compounds, but they share at least one element in common, you can get still a single product. In which case, if these compounds as products are made up of three elements, they are called ternary compounds because that is a term representing three, just as binary represents two. So we have a few more examples here. Sodium and chlorine will react with each other to form sodium chloride. Again, this is a binary process since we have a single element of sodium, single element of chlorine forming a singular compound as a product. We have a few more examples. I'm going to jump one here and show you how hydrogen reacts with oxygen to form a singular compound of water. And here's a repeat of our sodium chloride. Now, one that's a little different and will not come up very often at all is the process of photosynthesis. Now, in this case, we do have one thing in common with previous page in that both of these compounds that are reacting share an element in compound, namely oxygen. But we actually do have two products. We have one main one, which is glucose, and we also have a waste product of oxygen, which of course we are quite thankful for. This is one reaction that's an exception to the rule. And the question you might be asking as well, if it's the only one that does not have a single product, how do we know that it's synthesis? Because it's in the name. Photosynthesis. Now, just as two reactants can merge together to form a singular product, the reverse process can happen as well, and that one is known as decomposition, in which case decomposition will always, without question, always have a single reactant, and it must be a compound. And what will happen is that compound will then break down into its base components, into simpler elements, or sometimes simpler compounds. So for instance, we have a reverse reaction of the synthesis that we looked at earlier, in which case we have the compound water, a single compound, single reactant, using electricity passing through it, will break it down into its base elements of oxygen and hydrogen gas. Here we have the ternary variety, in which we have the compound calcium carbonate. When heat is applied to it, it will break down into two different compounds, binary compounds, calcium oxide and carbon dioxide. So in both cases, a single compound as a reactant breaks down into two different products. So here we see, once again, decomposition at work, and here are a few more examples. So we've got hydrogen peroxide here breaking down into water and oxygen gas. We've seen electrolysis of water a few times already. Nitrogen triiodide can break down into its base components of nitrogen and iodine. And one that is very important in our modern society. So, all new cars, and for quite some time in fact, have been equipped with airbags. And whenever a crash of sufficient speed occurs, you see, airbags contain this compound right here, sodium nitride. When the crash occurs, an electric current is signaled to pass through this compound, causing a rapid decomposition. And what will result is there'll be some solid sodium forming, but also there'll be the rapid onset of nitrogen gas, which will rapidly inflate the bag. Faster than the eye can blink, in fact. Such a fast reaction. But that is the mechanics, the chemistry of how an airbag works, and how it can, as long as you're 5'2" or higher, save your life. Okay, so we want to look at a sample reaction here, predict the product, and write a balanced equation for the reaction of potassium with chlorine. Alright, so in this case, we know we want potassium to react with chlorine, and as we hopefully remember, chlorine is diatomic because it is on that list. I brought clocks for our new home. And remember, these 7 are the ones that are always going to be diatomic no matter what. And chlorine is on that list. So I've got to remember that. Alright, so I look through this. Potassium's going to react with chlorine gas. And I see 2 elements each reacting with each other, which leads me to believe this is probably synthesis. And, as we remember, potassium is a +1, and chlorine in its original state is -1. So this will give me a nice neat ratio of 1 to 1. The only thing I would still have to do after this point is balance. So I am deficient in chlorine on the right side, and now I'm deficient in potassium on the left side, and this looks like this should be my final answer. So I'm going to go ahead and check it, and we successfully identified this as synthesis. And we know the product was supposed to be binary, and I do see 2 parts to this, so that is indeed a binary compound. Okay, I've identified the ion charges, and it looks like, at the end of the day, everything matches up exactly as I predicted. So let's move on and look at the third type of reaction. So we've covered synthesis and we've covered decomposition. We're now going to move on to combustion. Now, combustion in your book, in your reading, may be a little misleading. I'm going to try to clarify a little bit. Combustion means one thing and one thing only. It means that O2 is a reactant. If one of the reactants is oxygen gas, it is automatically combustion. Where the confusion might stem from is there are certain types of combustion that are quite predictable and others that are not. And here's the predictable part. Whenever a hydrocarbon, and a hydrocarbon is exactly what you might think it is. It's something made of hydrogen and carbon. That's it. Sometimes these might also contain oxygen, but all hydrocarbons must, at minimum, contain carbon and hydrogen. Whenever these compounds undergo combustion, they always get the same 2 products. And as you can see here, when propane is combusted, and don't worry about recognizing the fact that this is a different name for what we might have otherwise learned as tricarbon octahydride, since that's an advanced lesson beyond the scope of this class. But all hydrocarbon combustion, so I'm showing propane and ethanol here, always result in the same two products, carbon dioxide and water. And I believe we've spoken about this before when we did balancing, since we identified these as odd-even types problems that can trip us up. But it doesn't matter what the composition of the hydrocarbon is, because in every case, see, we've got some massive hydrocarbons here. We've got pentane, and then we've got, I can't even tell you what these are called, to be honest. But in every case, it always results in the same exact products. And they'll always be balanceable as well. Okay, so at this time, we're going to allow a little bit of practice time. So I'd really recommend, as I go along this, you pause, you attempt it yourself, and then you look back as I try to show you how it works. Okay, so the first reaction says the reaction of butane, C4H10, with oxygen. So, C4H10, this says predict the products and write a balanced equation for each. Alright, so this one is obviously combustion since I'm reacting with O2. And as I literally just got finished saying, the products must be CO2 and H2O. Now hopefully at this point you remember the trick I taught you for balancing these things. So we'll take the subscript of the hydrogen and use it here. Now, that will require us to double the C4H10. That will require us to put an 8 here to balance out the carbon. And then all I'm left with is the oxygen. So I have 16 here, and I've got 10 here. So if I did this right, half of 26 is 13. So I've got 8 carbon on each side. I've got 20 hydrogen. And then I've got 26, and I've already counted the oxygen. So this one should be good. So this is a good example of combustion in action. Alright, I'm going to erase this. So again, now might be a good time to pause as you try number 2. Let's take a look at number 2, the reaction of water with calcium oxide. Okay, so this one I'm going to outright admit could be a little tricky. Now, calcium oxide is easy enough to put up as a compound since calcium's a +2 and oxygen's a -2, so it's a 1-to-1 ratio. Now, I've given you a hint here since I already admit that this one can be tricky. Water with a metal oxide, we have a metal oxide right here, metal and oxygen, makes a metal hydroxide, which means CaOH. Except, I need to follow the rules that I taught you. Calcium's a +2 and hydroxide's a -1. So I've got to reverse these and do my parentheses. Okay. And what am I left with at this point? Well, actually, this one is an example of synthesis. So, let's see if we can get this one balanced, and it appears to already be balanced. I have 2 hydrogen, I have 2 oxygen, and I have 1 calcium. Okay, so this was an example of synthesis, one of those ternary compounds we've talked about before. Alright, I'm going to erase this and advise you to pause again as we move on to number 3. Now, number 3 is interesting because as you do some of your assignments, we're going to discuss the fact that some of these could have more than one classification. So let's look at it. We've got the reaction of lithium with oxygen. I hope you didn't forget that oxygen is on this list of the 7 that are diatomic, meaning oxygen must always be O2 when found in nature. Okay, now, here's the tricky part that I was alluding to. There's more than one way to classify this. So, first off, you have a single element and a single element reacting with each other, which would lead you to believe that it's synthesis. And that is correct. But I also said earlier that combustion means one thing, and that means that O2 is a reactant. So this particular reaction actually has two different classifications to it. It could be synthesis or it could be combustion. If on a question, homework, quiz, test, whatever, I ask you to classify this type of reaction, either one would be acceptable. I would not require you to put both down. But let's go ahead and finish this. Now, lithium is a +1 and oxygen is a -2. So I'm going to reverse these and I'm going to get Li2O. And of course, the next thing I would expect is balancing. So I was deficient in oxygen on the right side, so I put a 2 in front of the lithium oxide, and that made my lithium go up, so I put a 4 here to fix that. Alright, one more time, I'd advise pausing, so we can go ahead and get a look at number 4. It's time for a decomposition reaction. Okay. Decomposition of carbonic acid. Now, we already know decomposition means only one reactant, so I can go ahead and with confidence say that. Now, I can definitely admit you would be confused looking at this, wondering, well, wait a second, how am I supposed to know what the products are? Well, that's why I've given you a hint yet again. Carbonic acid is found in soda, and when it breaks down, it's probably going to produce something that is very characteristic of soda. And if you were guessing those bubbles, carbon dioxide, you would be correct. That leaves us with the question of what is the other product? Well, again, could be tricky, but we notice we have as a reactant a ternary compound, which means both of our products must be binary, so 2 parts. So the only thing I still haven't used is hydrogen, and hydrogen is more likely to bond with oxygen than carbon, as we've seen time and time again, so it's probably a safe bet to say that the other compound should be H2O. A little tricky, I'll admit, but we'll get there. Okay, so let's balance it, and that was easy. Awesome. Okay, let's move on. I've got a few more practice problems, so let's see if we can try to work through these. So again, I would advise pausing as we go along these so you can kind of try to work them out yourself. Alright, number 1. We've got pentane reacting with oxygen. Well, we know what that means. It's combustion. Anytime a hydrocarbon is combusted, we get CO2 and H2O. Alright, let's do the trick. We'll use the subscript from hydrogen in front of the water, and then we'll use that to double our hydrocarbon because the hydrogen has been doubled. Alright, from there we'll put up our coefficient for carbon dioxide, and I have 20 oxygen and 12 oxygen, which adds up to 32. Half of 32 is 16. Okay, which means I have to simplify. Alright, let's check to make sure that that went all right. Remember, if you can simplify your coefficients, you must do so. So I've got 5 carbon on the left and 5 carbon on the right. I've got 12 hydrogen on the left, 12 on the right. I've got 16 oxygen on the left, 10 and 6 on the right. Okay, looks good, looks good. Okay, next up we've got water reacting with potassium oxide. Let me just double check here. Let's see, potassium is a +1 and oxygen's a -2, so it looks like I balanced that out properly. And now, there was a hint about this on the last page, wasn't there? Let's see. Water with a metal oxide makes a metal hydroxide. Okay. So, metal hydroxide. So, it should be KOH. There's my metal hydroxide, just like number 2 on the last page. So next up, I should probably balance, and that should be fairly simple. All right. Very nice. Okay, next up, we've got another one that could qualify as two different types of reactions. Calcium reacting with oxygen. Okay, so calcium's a +2, oxygen's a -2, CaO. It's synthesis, or it's also considered combustion. Let's balance, and we're done with that one. Decomposition of sodium chloride. That's not so bad. It's binary. It's going to break down into its base elements. Don't forget that chlorine is diatomic. And that one's done. And finally, a reaction that I'm sure at this point all of us care quite a bit about, since octane is the primary component of gasoline. Wouldn't go very far. Granted, right now, gasoline's cheap, and we're not really supposed to go anywhere, but I digress. Okay, combustion. We'll add O2. We'll get our usual products of combustion of a hydrocarbon, and now I'll go ahead and do my trick to balance. Put the hydrogen subscript as a coefficient, double the hydrocarbon, fix the carbon dioxide, and from there finish off the oxygen. So I've got 32 and I've got 18, which, unless I fail at math, which I very well could, adds up to 50. So that should finish up the first three types of reactions. Okay, that means that we have two reaction types left to go. And they're both related to each other. They are called single and double replacement reactions. Another name that they go by, which I tend to use more often, is single and double displacement. It's just like tomato, tomato. It means the same thing, it's just a different way of saying it. But on this page, you can see what the overall reactions look like. In single replacement, you have an element reacting with a compound, and something exchanges. In double replacement, you always have two compounds reacting with each other, and partners will trade. Okay, so let's look at single displacement a little bit more in depth. Remember, again, also called single replacement. So we have an element reacting with a compound. In this case, aluminum is reacting with copper 2 chloride. And in this case, the aluminum will replace the copper, and the copper will now go solo. How do we know those are the two that are supposed to trade? Because they're similar types of elements. So let's look at it. Aluminum is a metal. Copper is a metal. Chlorine is not a metal. So it's only ones that can consider trading with each other are aluminum and copper. You can also think of it as aluminum is a cation. It's positive. Copper is a cation, but chlorine is an anion. So the similar types have to trade with each other. And here is the reaction displayed for you, shown what it would actually look like. But the thing with single displacement is it won't always occur. You have to check if it can. And that's where we make use of this, what is called the activity series. It ranks how active each of these elements are. Now, if you're worried about having to memorize this, don't, because it will always be given to you on a test. Now, you'll also notice there are actually two different series, one based on metals and one based on halogens. Now, the halogen one is easy enough to remember. Fluorine is the most active and iodine is the least. So, the top of the list are the most active elements, the bottom of the list are the least active. So, if something is going to replace something in single displacement, the lone element must be more active than the element trying to be replaced in the compound. Now let's take a look here. So first off, we're considering magnesium reacting with aluminum chloride. Can it happen? If it's going to, Magnesium must be more active than aluminum. Let's check the activity series and find out. Is magnesium more active than aluminum? Yes, it is, because magnesium is higher on the list. Just barely, but this does qualify. Magnesium can replace aluminum. And I don't know if this is called, got ahead of myself there. Okay, the reverse, however, will not happen. If aluminum is trying to replace magnesium, aluminum is lower on the list than magnesium. It is not active enough to actually succeed at replacing magnesium. So the answer, if I gave you this type of question, would be no reaction. And I think it's called the reflexive property of math or something, but if you reverse them as reactants, or maybe it's the commutative property, it's one of those, it doesn't matter. It's always looking at, can the lone element replace the bonded element? It doesn't matter what order you put them in. If they're both reactants, it just will not work. So let's look at a few more. We've got iron trying to replace copper 2 chloride. I'm going to go back a page and see. So iron is here and copper is down here. So can iron replace copper? Yes, it can. Yes, it can. And we would get the following reaction: iron 2 chloride and copper. Next up, we've got zinc with nitric acid. Now, this one could be tricky because we don't all have the same type of elements. Zinc is a metal, but it's a cation. Then we come over here. We've got hydrogen bonded with nitrate. The nitrate is a -1 and the hydrogen is a +1. So it's the zinc and the hydrogen we're going to be looking at, since they're both cations, both positive ions. I'm going to go back again and look it up and find that zinc is up here and hydrogen, I obscured it a little bit there, is right here. Can zinc replace hydrogen? Yes, it most certainly can. So we'll get zinc nitrate and hydrogen gas. Next up, we've got a halogen one. Magnesium chloride and bromine. Alright, so can the bromine replace the chlorine? No, it can't. Bromine is less active than chlorine, just barely, but this is a no reaction. So, let's look through this. We're going to do an example here. Magnesium is added to a solution of lead 2 nitrate. Can it happen? Well, what are we considering here? The question is, can the magnesium replace the lead? Let's check. We're looking at magnesium and lead. Can magnesium replace lead? Oh, yes, it can. Okay, now, magnesium is a +2 and nitrate's a -1. And then the lead will be left by itself. Of course, the next thing I would expect is balancing, but fortunately, this one is already balanced. And this page just kind of illustrates that yet again. And as you see here, this is something important you may be expected to know. Whenever an alkali metal or an alkaline earth metal, so we're talking about group 1 and group 2 on the periodic table, is placed in water, you always get the metal hydroxide and hydrogen gas. So make sure you are aware of that fact. Okay, now we've got some practice here. We're going to look through it just like before. So I've given you the activity series here on the right. And let's work through it. Make sure you're pausing. Okay. Aluminum gets dipped into a zinc nitrate solution. Aluminum is dipped into zinc nitrate. And I know this is the formula, one, because we did it earlier, but also because zinc is a +2 and nitrate's a -1, so make sure that balances out. Can aluminum replace zinc? Yep, sure can. So I've traded the elements that are similar, and then next up I would expect some balancing here. Just like before, aluminum's a +3, nitrate's a -1, so I've done that. And if you possibly remember, the easiest way to fix a 3 and a 2 is to reverse them. So let's do it. And then I'll just have to fix the lone elements. As we remember before, you should save those for last. Okay, I'm not going to erase this one yet. I'm just going to write beneath it. And number 2, we've got sodium placed in cold water. This is exactly what I was talking about on that last page. What happens when an alkali or alkaline earth metal are placed in water? You always get the same products. You get the metal hydroxide and then hydrogen gas. Okay, so next up, let's get this balanced. And I think the best way to do that would be like such. So I was short in, well, I had more hydrogen on the right, but I had an odd problem here, so I doubled it. Then I fixed the water, and then I fixed the sodium. Okay, next up, number 3. I'm going to squeeze it in down here. Gold is added to a solution of calcium chloride. Okay, again, calcium's a +2, chlorine's a -1. Can gold replace calcium? No, it can't, because gold is one of the least reactive metals out there. It's called a noble metal in some cases, keeping in tradition with the noble gases, which are completely unreactive for the most part. So, the answer to this would be no reaction. That one was easy. So anytime you see gold as a single element trying to do single displacement, you pretty much know that's going to be the answer. Alright, I'm going to erase all this, and then we'll get ready to do the next 3. So hopefully everything's going all right so far here. Alright, let's check it out. Number 1, on the bottom, we got magnesium being dipped into a nickel 2 chloride solution. Alright, so can magnesium replace nickel? Sure can. The nice thing about this one is they both got the same charges. Magnesium is already a +2, so it'll do that. The nickel will be left by itself. No balancing is necessary since everything is balanced. Alright, let's move on to number 2. Lead is placed in a solution of iron 3 nitrate. Alright, let's see what we've got here. Lead is placed into iron. Uh-oh. Lead is not active enough. It will not work. No reaction. Alright, let's finish up. Number 3. Zinc is added to a solution of copper 2 sulfate. Sulfate is a -2, so it's going to balance nicely with the copper. Alright, let's check it out. Can zinc... Where is zinc? Why am I up? There it is. Zinc. Can zinc replace copper? Yes, it can. And zinc, like the copper in this case, is a +2. So, ZnSO4 plus Cu. And nice and balanced. So that's single replacement in a nutshell. Alright, let's finish off with double displacement. And like I alluded to before, double displacement means two compounds reacting with each other and everything will trade. And the nice thing is with double displacement, at least for the purposes of this class, one thing will always have to be more active. So it will occur. You will not have to check the activity series in order to finish it. Period. Alright, so two compounds will exchange ions and form two new compounds. Now here's something you will need to know. I'll probably ask you about. Whenever double displacement occurs, one of the products must, absolutely must, be one of these three things. A solid precipitate, a gas, or a molecular compound like water. So here's an example. We've got hydrochloric acid reacting with sodium hydroxide. Kind of like in foil, the outside and the inside will trade. So we end up with NaCl and water, which for some reason was rewritten as HOH, but it is in fact water. So here we see lead nitrate reacting with potassium chromate, forming lead chromate and potassium nitrate. As I mentioned back here, one of these three types of compounds must result. In this case, we can clearly see a bright yellow precipitate, nice and poisonous as well, but it satisfies the fact that this was indeed double displacement. We see a very pronounced white precipitate in this particular reaction when silver nitrate reacted with potassium chloride. So again, we formed silver chloride, and then we formed potassium nitrate. And one more example, yet another precipitate example. Back here, the special type of compound that was formed was a molecular compound. It was not a precipitate, but here, again, it is. Lead chloride reacts with potassium iodide. The lead combines with the iodine, since they are on the outside. The chlorine combines with the potassium on the inside, thus giving us potassium chloride and lead iodide, a precipitate. Final page. This is your reference chart. This is all of the reactions you're expected to know, all put together. So, when synthesis or combination or composition occurs, you have something reacting with something and they merge. Decomposition, the exact opposite. Single displacement, also known as replacement, make sure you check the activity series. Element reacts with a compound, and if possible, the element replaces the corresponding part of the compound that it matches. Double displacement, compound reacts with compound, everybody trades partners, no need to check the activity series. Combustion, I'm going to jump ahead just a little bit here. We've got just means O2 for just combustion. But if it's of a hydrocarbon, then products must be the same, carbon dioxide and water after reacting with oxygen. And one special type of double displacement I'd like you to know about, but I might only ask for bonus, is called neutralization, in which an acid, which must be a compound, reacts with a base, which must be a compound. Always results in the same two compounds, salt and water. And that is the finale of Chapter 8. We're going to move on with some exercises for this and go from there. Thank you all. Please continue to be safe.